think the stream, yeah, okay. I think the stream is up now, and I think we're recording as well. Um, just doing a quick audio check. Can you hear me? All right, so we were running into some really stupid computer issues just a moment ago, but hopefully it's settled now. Okay, so topic is Lagrange multipliers today. Oh, you're kidding me. It's always something. I need to get my OBS up and running. Just a second. Okay, I think we're good now. Okay, so the topic is Lagrange multipliers, and they're sort of confusing the first time you learn about them, because it involves a lot of notation, right? It's kind of hard to think about. But I think hopefully after an explanation like this, we're going to go through like the motivation between why it works, and basically do everything other than the computation, which at the end of the day, you got to know how to do yourself, right? And unfortunately, the problems being chosen here can sometimes be super nasty, which we might see in a moment. But at the very least, I hope to get you really solid for the concepts. So the motivation of the Lagrange multiplier is you want to maximize some function f subject to some constraint g of xy is equal to k. And for now, we're just going to use functions of two variables, xy, just to keep it simple. But it extends perfectly fine to functions of three variables and so forth. So far, so good? Just tech issue-wise?
Yeah.
Okay, great. So I'm following Paul's online notes, this lamar.edu page that usually has really good stuff, or pretty much always has really good stuff. I just think it might be a little bit dense for intro students, and maybe to turn some of these examples into video form. But also come up with some explanations of my own. So one of the examples here, like maybe a simple one, is to imagine the constraint g of xy being equal to k as just like a circle, right? Let's just choose it to be a circle for this example. And let's say f of xy is something that has level curves that look more or less like parabolas. So this level curve is where it's equal to -4, this one is -3, -2, -1, and so forth. Seem good enough so far?
Yeah.
And the sort of insight behind Lagrange multipliers is that this is the kind of key system of equations to solve, where gradient of f is equal to lambda gradient of g, and the function g is equal to k. Right? So these are sort of your system of equations to solve in order to find critical points, basically. So I think that this equation right here is probably a little bit mysterious. Whereas this equation right here, I hope, is reasonably self-explanatory, right? Like if you're being constrained to exist inside a circle, and the circle equation is represented by g of xy is equal to k, you just kind of write it down as part of your system of equations, right? Seem hopefully no objections? Yeah. Okay. So I think the really thing to discuss is just what the heck this is saying, where gradient of f is equal to lambda gradient of g. Like this is sort of what it all comes down to, right? And the way to think about this is, let's maybe just choose some other point of intersection, like right here. Yeah? And let's say that's this function keeps going so that the next one turns into 0, right? Level curves. It should be pretty apparent just by looking at it that this is not going to be a critical point, maximum or minimum, right? Just you can kind of see, because like over here it's -2 and over here it's 0. So like it should be kind of clear that this one over here is not going to be a minimum, right?
Mm-hmm.
And the way to kind of see this in a slightly more quantitative way, is to think about essentially partial derivatives. Oh, come on now. Whatever. Sometimes you accidentally delete something and it just completely disappears and you can't control Z it. It's very odd. Okay, so we have some point in question here, and the basic idea is, okay, if we go a little bit in this direction or a little bit in this direction, right, sort of tangent to the circle at that point, Uh, because this level curve is sort of like intersecting it and going right through it, we sort of can be sure that one of these two directions will make the function smaller, minimize it. Or sorry, make it smaller, which means at this point can't be a minimum because just a little bit next to it has a smaller neighbor, right? Does that make sense?
Yeah, I can see that.
Yeah, like if you're at a point, let's say instead of temperature, let's say we're, the hills are basically shaped like this, right? These are the contour lines of the hill, and for whatever reason, you're bound within the circle, right? It's like saying right here, just the fact that you can see it sloping downwards should make it pretty clear to you that you're not at a minimum right now. Right? Or like the fact that it's sloping downwards in a direction that you're able to walk means that you're not at a minimum. So, okay, with that in mind, now let's think about this point right here. And like just kind of intuitively looking at it, we can kind of see that this point is probably going to be the global maximum for this function with this constraint, right? Because it sort of is the only point that sort of achieves this -2 line, whereas everything else sort of has a larger value, right? Like -1 or 0. So like what's the like exact calculus condition for this? Like how would you describe that? How do I put it? Let's sort of talk about the arrows like before, right? If you just go a little bit to, the left or a little bit to the right, basically just, a little bit in either direction tangent, right? This is sort of saying that, how do you put it? This is essentially saying that because the tangent lines of this curve match up with the tangent line of the constraint, you sort of have this situation where, if you're just moving a tiny infinitesimal amount to the left or right, you're not going to be getting any smaller, basically. The only way you could get smaller is if you actually like walked outwards, which you're not allowed to because you're constrained to the circle. So this is basically to say that the condition in question here is when the tangent line the tangent line of the function at a point is parallel to the tangent line of the constraint at that point. Does this explanation make sense so far?
Yeah.
Yeah. So how would we express using calculus that the tangent line of this curve, right? This, this is ultimately a curve, a level curve of the function f, and this is, the function g. I guess g is equal to k. So using calculus, how would we express that the tangent lines are parallel at this point?
Is this where the lambda comes in?
Yes, exactly. So one way of saying that, okay, so basically this is saying that if the tangent lines are parallel to each other, right, that means that the sort of gradient, right, the sort of orthogonal vectors are also parallel to each other, which is basically saying the gradient of f has got to be equal to the gradient of g times some constant scalar, right? They could be pointing in the same direction or opposite direction. All you know is that they're parallel to each other. But let me repeat this again. Because we know that the tangent lines have got to be parallel to each other, the tangent line of the level curve and the tangent line of the constraint, this means that the gradients of the tangent line and constraint also have to be pointing in parallel directions, right? Because the gradient is sort of like a normal vector, right? It's kind of 90 degrees orthogonal to the tangent. So far, so good?
Yep.
Okay, great. So this is basically the justification right here for Lagrange multipliers, right? This, I guess this little 9-minute explanation, this little visualization. But the idea here is this is basically a system of two equations, right? Because there's going to be, like, rewriting this basically turns into a fx at some particular point. Well, let me put it this way. Fx at x comma y is equal to lambda times gx. This is the partial with respect to x at x comma y. And the exact same thing with the, the exact same thing with the partial derivative with respect to y. And then again, we sort of just import the constraint one more time. Gxy equal k. So at this point, this is a system of 3 equations and 3 unknowns. The 3 unknowns are going to be lambda, x, and y. And in principle, this is solvable. Sometimes it's computational, really, really nasty, and you can't get an exact answer. But like 3 equations, 3 unknowns, unless you messed up somewhere, or sorry, unless their system is set up improperly to where there's no solution, you should be able to work this through, right? And they're probably not going to ask you any trick questions that that don't have a solution. But does this make sense? Like at this point, it's going to look like a genuine system of 3 equations, and it might be a little bit nastier than you're used to from high school. But in principle, it's algebra at this point onwards, and you're basically trying to solve for the values of x and y. Sometimes you have to solve for lambda. Sometimes the lambda cancels out. You don't really care too much about lambda, to be quite honest. It's just a sort of tool that lets you, I don't know, it's sort of like the glue that makes things work. But you don't, there are questions where you have to find it, and there are questions where it cancels out and you don't have to care about it. But the computation for these kinds of problems can go in a lot of different directions, and sometimes it's kind of annoying, right? But this is the gist right here. Okay, so some other things I wanted to mention are just sort of covering my bases, right? Using Lagrange multipliers, you kind of have to make sure that if you're looking for a minimum, that the function actually attains a minimum on the constraint in question. Like, how do I put it? Like, if you had no constraint at all, right? If your constraint was that g of x comma y, if you just didn't have that constraint, right, that basically means the circle would disappear. And then at this point, you would say that there really is no minimum because this function can just keep on getting more and more negative, right? So you need to kind of be sure that whatever system you throw the Lagrange multiplier at has a minimum in the first place. Otherwise, it might spit out a nonsensical answer. And what else do you got to do? Once you do get an answer, or sometimes multiple answers, right? This process basically finds a bunch of critical points for you. You know, sometimes it's 1 critical point, sometimes it's 2 or 4, or 3 or whatever. You have to go through and actually do a bit of a sanity check, right? Because like right away, it's hard to tell whether something is a minimum or a maximum. You kind of have to plug it in and check it against its neighbors a little bit, right? So if you want it to be thorough, let's say that the Lagrange multiplier method spit out this point right here. I would probably want to check its neighbor somewhere around like here, right? I would probably just want to manually check that the temperature at this point is lower than the temperature at that point, or elevation, or whatever you want to call it. What else? Yeah, so like there's just a lot of like elbow grease you got to do, unfortunately, for these kinds of problems, and we'll show you a little bit more detail. But in terms of other motivating things, I think that this is almost always the common explanation when you first introduce Lagrange multipliers, is drawing these sort of tangent lines on this sort of contour plot. But whenever I learned it this way, I found that I would always forget it. And it really wasn't until I took a graduate StatMech course where my professor there actually gave us a really neat way of looking at the Lagrange multiplier slightly differently. But, you know, it's mathematically equivalent and it'll result in the same system of equations. But like motivation-wise, I think it's a bit easier to see where this is all coming from. So what this method is, you know, it's like, maybe call it an alternate method. It's basically saying, all right, instead of trying to remember that to set, you know, gradient of f is equal to lambda gradient of g, let's try to do something clever and sort of fold the constraint into the function. And what I mean by that is, let's let g, capital G of x comma y, be equal to g of xy. minus k. And that's obviously equal to 0 because we're just moving the k to the other side via subtraction, right? So the kind of clever thing to notice is that if we let x, like a different function, capital F, that's a function of x, y, and lambda, if we let this equal to f of xy minus lambda of g of xy, well, g of xy is just 0, right? G of xy is 0. So really what this is we're just taking little f of xy and adding or subtracting 0 to it, which is like totally a thing you can do, right? You can always just add or subtract 0. Yeah?
Yeah.
So instead of optimizing for little f, we can sort of optimize for big F instead. We can think about optimizing for big F instead. And at this point, we're just saying, okay, let the gradient of big F, that's a function of x, y, and lambda, let's just set that equal to 0. And at this point, the analogy to one-dimensional calculus becomes a little bit more clear. We're like literally just trying to find the critical points, the values of x, y, and lambda, that make the gradient, which is the multi-dimensional equivalent of a derivative, equal to 0, right? In single variable calculus, you would basically do, you would basically just say, okay, we're trying to maximize something. Well, let's just take the derivative and set equal to 0. And as just a sanity check, let's, let's make sure that it's actually a minimum or a maximum by comparing to points near it. And let's check the boundary points, right? And that basically motivates the Lagrange multiplier method, where you you sort of do this like little piece of calculus, and then you also got to do the little pieces of sanity checks at the end. Like, does this analogy kind of make sense?
Yeah, I see that.
Yeah, okay. So this way is sort of how I wish it was presented to me, because I kind of forget the visualization every single time. And all I remember is this like weirdness of this like gradient of little f is equal to lambda gradient of g. And that doesn't make a lot of sense to me. What does make sense is using this little trick to just say, okay, trying to optimize big F, just take gradient of big F equal to 0. And let me show you why this is mathematically identical, right? Because, okay, then the gradient of big F is just equal to df dx, df dy, and df dz, or sorry, d lambda, rather. And you're going to be setting each of these ones equal to 0. 0, 0, 0. So then df dx, you can see that df dx is going to be equal to, so df dx is basically equal to d of little f dx minus lambda of dg dx. Notice that this is lowercase g. It doesn't really matter too much because lowercase g and capital G only differ by a constant, right? These two functions only differ by a constant, so their derivative with respect to x or y is the exact same thing. But this is basically saying df dx minus lambda dg dx is equal to 0. And that's sort of like saying, oh, look, that's exactly what we had over here, right? I just used a slightly different notation, but partial of f with respect to x is equal to lambda times partial of g with respect to x. You just got to move this to the other side via addition. But this is the exact same concept, And what's kind of nice about this is that, okay, so this is the df dy equation as well. I feel like it motivates the constraint a little bit more, because the last expression is df d lambda, which is just df d lambda, basically the partial derivative of f with respect to lambda is just g of xy, right? So df d lambda is equal to g of xy, capital G, and that's just got to be equal to 0. And what was g of xy? That's basically just lowercase g of xy minus k is equal to 0. And you can see that this is equation 1, equation 2, and equation 3. And that's exactly the same as equation 1, equation 2, and equation 3 here. And what I like about this sort of alternative way of thinking about it is that it sort of puts x, y, and lambda on more or less equal footing, rather than kind of treating this constraint as a little bit special and then adding it in at the end kind of separately from the calculus, right? This way of doing it, it kind of incorporates the constraint into the calculus, so to speak. Anyways, I just really like thinking about it this way, and it found that it helped make it click for me, and I hope that it makes it click for somebody else. But you can see that once you get to this point, the problem becomes the same either way. You just got to solve a system of 3 equations and 3 unknowns. Okay. So conceptually, I think that's about all I have to say. Shall we move on to some problems, or are there any conceptual questions? Feeling okay?
Yeah, we
Nice.
should.
We can move
Yeah.
on.
Gotcha. I hope this was helpful. I think,
Yeah, no, that explained a lot.
yeah. Okay, so let's take a crack at some problems, yeah? And I think one of the problems here, I won't solve it all the way through, but we're talking about a rectangular box. Right, a rectangular box with the volume is equal to x, y, and z. Excuse me, why am I using commas? X times y times z. And the length is, the constraint. Let me put it this way. F of x comma y z is the thing we're trying to optimize, and that's just equal to the product. And then g of x, y, and z is equal to what is it defined as? It's just x plus y plus z is equal to 96. Oh, sorry. Let me be a little bit more specific. It says that a shipping company handles rectangular boxes, provided the sum of the length, width, and height does not exceed 96. So one of the very first things we need to do is try to deal with this inequality right here. And I would say it's actually not so bad, right? If we're trying to maximize, the problem is asking us to maximize the volume subject to this constraint right here. And you can kind of mentally imagine, all right, what if x plus y plus z didn't use up the entire like 96? Let's say we're only using 95 inches, right? Like, is it possible that the absolute global maximum is attained by some situation where x plus y plus z is equal to 95? And, well, not really, because if this is not quite equal to 96 and you've got an inch left to spare, well, I would say just take one of these dimensions, x or y or z, it doesn't really matter, and just crank one of them up by an extra 1. And that will only make the volume get bigger, or at least it will stay the same, right? It's not going to make it any smaller, basically. So by that kind of argument, we can kind of argue that we don't have to think about an inequality. We can just think about a tight equality where it's equal to 96. Does that logic make sense?
Yeah, okay.
Yeah. I was being a little bit slippery there because technically, if one of these is equal to 0, then 95 or 96 doesn't, it's going to be the same either way. But it should be pretty clear that it's going to kind of absurd. Like, if one of these is equal to 0, the volume is going to be equal to 0, and that's clearly not, the optimal case. Right? But, this is probably not a proof-based class, and you probably don't have to argue that carefully. But I hope it's relatively intuitive that the maximum is going to be achieved when we let it be exactly equal to 96. Or at least, it suffices to just think about equality rather than having to think about smaller numbers like 95 or 94. Okay, so far so good, right? Now let's go ahead and just do exactly what we were saying earlier of using the Lagrange multiplier method. So we're going to set the gradient, equal to the other gradient times lambda, and then we're going to just pull in the constraint afterwards. So what does this look like? F of x, del f is just equal to yz, xz, and xy, I think. Whereas del g, by the way, have you heard of the symbol? I call it del sometimes. I guess it's just a nickname, a fairly common nickname, but just don't be confused if you hear that. But this is just 1, 1, 1, right? Because this is just the partials of x plus y plus z. So this is basically saying yz is equal to lambda, xz is equal to lambda, xy is equal to lambda, and x plus y plus z is equal to 96. So far, so good?
Mm-hmm.
Well, this is a system of 4 equations and 4 unknowns. So at this point, I don't want to say too much more, because I think it's always good to leave the solving to the students, right? But, in principle, you should be able to find maybe more than one possible set of x, y, z, and lambda values that satisfy this system of 4 equations and 4 unknowns. And like I was saying before, you kind of got to do a sanity check, right? I think if off the top of my head, you might get that. What was it? You might, like, one of the critical points that you might get is like 0, 0, and 96, right? And clearly this is, a minimum rather than a maximum, because the volume is 0, right? So
Yeah.
points like this are not going to be so helpful. You're looking for instead a XYZ triplet that kind of makes sense and maximizes the volume, and kind of intuitively, right? We know in 2 dimensions, I think it's a pretty common fact from high school, that the volume of a rectangle is maximized, subject to when you only have a total amount of perimeter, right? What exactly was the question? Like in high school, you probably at some point learned that, if you only have a total amount of like 100 yards of fence, for example, and you wanted to make the largest possible area, choosing it to be a square is the best way to maximize the area, right? And
Mm-hmm.
just sort of extending this into higher dimensional thinking, you'd kind of expect the same symmetry to apply, right? So you got to do the work to justify it, but I think you can use that as a bit of a sanity check, I hope. What else did I say? Oh, I should have said this at the very start of this problem, but we should have also done that other sanity check at the start, where we can actually expect we can actually expect to find a maximum, that it's not just unbounded, right? And I think that should be pretty physically intuitive, where if you only have 96 total inches to work with, I don't think you can make like an infinite volume box, right? Like, that should be pretty clear. So
Yeah.
like the rigorous way to argue is that because the XYZ domain here is a closed bounded set by the extreme, and because this is continuous, by the extreme value theorem, you can guarantee that a maximum and minimum exist. That might be a little bit overkill, but that's how you do things if you wanted to be careful. Extreme value theorem. And this is kind of intuitive, right? It's saying that if there's no like weird holes in the domain, and that the function is nice, it's basically saying it'll achieve a maximum and a minimum. Yeah. So hopefully that should feel pretty good about this one. The computation's not too bad. You should, if it were me, I would probably start by saying, okay, well, let's just set yz equal to xz, because we know that they're both equal to lambda, right? And do yz minus xz is equal to 0. And this tells us that this tells us that z times y minus x is 0. So either z is equal to 0, which is absurd. I mean, it can be. We just obviously know that that's not going to be the maximum we're looking for, right? But otherwise, x is equal to y. And then once you know that x is equal to y, you should go back to maybe another pair of these 2 equations and then try to figure out if you can nail down what z has to be. So maybe proceed like that, okay?
Okay, thank you.
Yeah. So I'll, leave it as a hint and leave it to the students. Like, I know that, like, sometimes just leaving students with, 4 unknowns, 4 equations, go ham is a little bit scary, right? But I don't want to do all of it. Okay. Any other questions I can address for this first problem, or shall we move on?
So quickly, so for the dimension, we only allowed to have integers. We
Oh,
cannot like have that.
dimension?
Yeah.
This thing right here? Not necessarily. I mean, you could have had like 95.5 or like 95.6 or anything like that. I didn't mean to mislead you earlier when I was talking about 96, 95, 94. I was just coming up with smaller numbers off the top of my head. But the argument that you can replace this inequality with a strict equality is true whether or not you want to think about integers or, all the or all the real numbers in between as well. Hopefully that makes sense either way, right?
Yeah.
Because if you're anything shy of 96, like 95.999, well, like, why not use that extra piece of length you got and crank up one of these dimensions by a little bit, right? It can only help. It's not going to hurt.
Yeah, all right, thank you.
Yeah. Okay, so far so good?
Yes.
Okay, so problem 2 is where things start to get really annoying. But the constraint, which is g of x, y, is x squared plus xy plus 2y squared equal 1. And if you plot this on Desmos, I believe it looks a bit like a tilted ellipse. So you would kind of expect, the distance, the shortest distance to be like there, and the longest distance to be like kind of that. But, at least when I took a glance at it, this one's kind of a pain in the butt to find. So first things first, what is the function you're trying to minimize or maximize? Well, okay. That's just the distance function, right? What's the distance function? In terms of x and y. Let's call that d of xy. Not a trick question. What is it?
X squared plus y squared.
Yeah, or the square root of x squared plus y squared, right? But one of the tricks to these problems is that because the square root is really, really nasty, hopefully you've seen this trick before in this class, but instead of optimizing d, maybe optimizing d squared instead makes your life just a lot easier. Because it should be pretty clear that comparing square root of x squared plus y squared and x squared plus y squared, it should be pretty clear that a maximum for this is attained when and only when a maximum for this is obtained, right? Like the square root function is monotonic and increasing, which is why it's sorry, that's a bad way to put it. Yeah, is that intuitive enough, or should I talk more about that? Have you seen this trick before?
I haven't, but that makes sense.
It makes sense. Good. Okay. Yeah, it just makes your life a lot easier not having to deal with the square root. Just remember that for your final answer, you have to, if we optimize d square and subject to g, at the very end, we're going to need to go back and take the square root of it to figure out the actual distance, right? But that's just a tiny step at the end. So yeah, let's do our sanity checks, right? It's sort of an oval is our constraint, so it should be pretty intuitive that there's going to be a minimum distance here and a maximum distance, right? I don't think we need to get too into the weeds of the proof on that. You can just kind of imagine that, like, as you sort of, spin like spin around the ellipse, there's going to be a point where you're closest and a point where you're furthest, right? It's kind of like the Earth orbiting the sun. It's more or less an elliptical orbit, if I remember correctly. And we talk about a day when the Earth is closest to the sun and a day when the Earth is furthest. So yeah, I think that covers our basis for what we need to do ahead of time. So now we're trying to, let's maybe call this, instead of d squared, let's call this, I don't know, capital F maybe? Or maybe let's just call this like regular f. Yeah? So using the Lagrange multiplier, gradient f of, you know what? So gradient f is equal to lambda times gradient of g. And this basically just turns into 2x is equal to lambda. Okay, what's the partial of this thing? 2x plus y, right? Yeah, the partial of x is 2x plus y. And then 2y is equal to lambda. I'm just sort of... I'm basically just carrying out the derivative and just writing it out in one step. But I think that's 2... what does this become? That becomes x plus 4y. Yeah. And then the constraint, we're pulling it in from before, is x squared plus xy plus 2y squared is equal to 1. So, yeah, 3 equations and 3 unknowns. X, y, and lambda are your 3 unknowns. So with something like this, you basically just gotta go through and start crunching through the pain, essentially. It kind of sucks, to be honest with you. I think just looking at it briefly, I would probably try to isolate... What would I even do? I think what I did was... y is equal to x and lambda. Y is equal to... Damn, that sucks so much. What's a non-painful way of doing this? Yeah, like the problem... Solving this out kind of sucks, and I didn't do it all the way. I'm just trying to sort of look at what the easiest approach might be. And gotta be honest, it kind of... all your options kind of suck. You could kind of imagine multiplying the top equation by 4. You know, both left and right by 4. And then just trying to subtract through and cancel out the y terms on the left-hand side. At which point you can solve for y in terms of x and lambda. So y in terms of x and lambda. And then you can plug that into this bottom equation. Yeah, I think that'll do the trick, but this might just have to be something you play around with a bunch. Try to see if you can turn this last equation all in terms of just one variable, whether that variable be x or lambda or whatever. Just see if you can isolate that.
Okay, thank you.
Yeah. And then try to solve for lambda. And from once you have lambda, you should be able to solve the others. Yeah, this is one of those things where it sucks. I plugged it into a calculator, Lagrange Multiplier calculator, and it's not pretty. And just off the top of my head, without having done it myself, you would just have to try out a couple of different areas to get some cancellation. Yeah. Okay. Is there anything else to say about that problem that I can actually, help with conceptually? At the very end, like I said before, you gotta do some sanity checks and make sure that the values you have are, actually maxima and minima. But you should be getting like 2 sets of like x1, y1, and lambda 1, x2, y2, and lambda 2. In fact, I think you might even get like 4. Excuse me. I think you even get, in fact, 4 sets of solutions. So like x1, like 1, 2, 3, 4, and those are probably going to correspond to the 2 closest and the 2 furthest. And you just got to do like a sanity check to remind yourself which one's which. And you do that by plugging it back into the equation f and seeing which one's larger and which one's smaller tells you which one is a maximum or a minimum. Yeah, this bugs me. I feel like there should just be a clean way of looking at it to get some cancellation, but it just seems like a total slog. And I don't feel good about that. Yeah. Anyways, shall we move on to problem 3?
Yeah.
Yeah. So at this point, it's basically the exact same idea. So we're just going to sort of go through the setup again. But the idea is x is labor, right? And y is capital. And we have a situation where I believe they're saying 100x plus 200y is equal to 20,000 is our constraint. So this is g of x and y. I wonder if some of these problems would be easier without using the Lagrange multiplier method, but I find that hard to believe. Yeah, maybe we'll play around with that idea afterwards. But, excuse me, where was I? Well, f is basically just whatever that equation was given. I guess they're calling it p instead of f. Is equal to 50 x to the 0.4, y to the 0.6, right? And, well, it's just basically routine at this point. You basically just take the gradient of p is equal to lambda times the gradient of g. And the gradient of p is, and here it's like 50 times. Oh, by the way, one thing that you can kind of do to simplify the problem a little bit is by maybe just dividing through by 100. So that turns into, I think, just x plus 2y is equal to 20. And it should be pretty clear that trying to maximize 50 x to the 0.4, y to the 0.6 is going to be, you know, the same values of x, y that maximize or minimize are going to work as well if you just get rid of the 50, right? So that can just make your life a little bit easier. Seem reasonable? What's up?
Would it be 200? Because
Would it be 200?
8,000.
Yeah, you're right. I think I missed a 0, right? You chopped me off 2 zeros? Yeah, you're right. 200. Thanks for catching that. But yes. Then this looks like 0.6, x to the 0.4, y to the negative 0.4. Right? So just set this equal to, well, what's the partial of g with respect to x? That's just 1, so this just turns into a lambda. And then you set you set this other one equal to, I guess, just 2 lambda, right? Because the partial of g with respect to y is just a 2. And then you multiply that by lambda. So I wrote it a little bit funny this time just because I'm being lazy, but this is your first equation. This is your second equation. And again, we have our constraint. And the idea is you're just going to try to solve for everything here. Yeah. This one might not be that bad now that I'm thinking about it, because you have this kind of nice behavior where 0.6, you know, is the same in both, except for one is negative. So you might try raising this equation to like some, here, let me write it out. I don't know, I'm just looking at it. X to the negative 0.6, y to the 0.6 is equal to lambda. Maybe try raising both sides to like, so if this is the 3/5 power, right? Maybe try raising everything to like the 5/3. So then that becomes like 0.4 to the 5/3. Times x to the negative 1, y to the 1 is equal to lambda to the 5/3. And maybe do something similar for this one too. And that should let you, between those two equations, that should let you do a bit of cancellation or substitution, right? Like, it looks at least like the x and the y are going to be pretty easy to manage if you do it that way. Because now they're not to some nasty power anymore. Yeah. Oh, in fact, just multiply them together, maybe, to solve for lambda. Yeah, right, because you would get like, so this is one equation, and the other equation is just like 0.6 to the, I guess you would have to raise it to the 5 halves power. x to the 1, y to the -1 is equal to lambda times 5/2. And then if you just multiply these two equations together, the x and the y just disappear, right? And maybe you can work with that, and that'll give you lambda. And once you have lambda, that should hopefully help you find something else. Got the gist?
Oh, okay, I see.
Yeah. So with equations like these, you kind of like got to start with an and, try to figure out the one that's easiest to solve, and try to, yeah. Oh gosh, I keep forgetting. At the very start, again, we should have tried to ask ourselves, okay, does it seem reasonable that there must be a minimum, or sorry, what are we trying to find, a maximum? Yeah, does it seem reasonable that, you know, there exists a maximum? And yeah, I would say so, right? Like not being a super careful proof, but just looking at x plus 2y, right? Your resources are kind of limited, and you know, it's hard to imagine this equation ballooning off to infinity when x and 2y can't exceed 200, right? Oh, it should also go without saying that x and y have to be greater than or equal to 0. I think this was true for all three problems we did today. No, I'm sorry. This was only true for problem 1 and 3. Oh gosh, I should get a drink of water. But for situations like these, x and y being greater than 0 is actually surprisingly important. Because if you didn't have this like implicit constraint, well, you could just get a very negative value of x, right, and compensate with a very positive value of y. Then x to almost, yeah, right. Wait, am I thinking of the right thing? Yeah, maybe. Actually, I'm not entirely sure. But the point is, I'm worried about this blowing up if you choose, if you're allowed to use like certain very negative and very large values of x and y. So things being constrained makes it, I think, relatively clear that it can't blow up to infinity. Seem reasonable?
Yeah.
Yeah. Yeah, I don't think this one is necessarily the worst. Yeah. Of course, work through these yourselves and make sure I didn't make some mistake somewhere, because I think this seems like a reasonable approach. I just oh, sorry, this should have been a 2 lambda, right? Is equal to a 2 lambda. So you gotta like make sure to, you know, I didn't do this super carefully. You gotta make sure to sort of look at this yourself and figure it out. Yeah, what's bothering me right now is that it seems like you can find, yeah, what's kind of weird to me right now is it's feeling like you can find the values of x and y using only these two equations, which doesn't seem right. You should definitely have to use the third equation somewhere, which maybe means that I did something wrong. But as always, play with it a little bit and see if you can figure it out. Oh, you know what might have been a more reasonable approach is maybe instead of trying to square things, maybe just take one of these equations and divide by the other to get rid of the lambda. And that'll give you an equation just about x and y. And then you can compare that to this other equation of just x and y, and that should let you solve for x and y. You see what I mean? Like if you had 0.4
okay.
x to the -0.6, y to the 0.6 is equal to lambda, and 0.6 x to the 0.4, y to the -0.4 is equal to 2 lambda. You can just divide the left-hand side and right-hand side by lambda. You also have to justify that lambda isn't 0 when you do that, which I think is reasonable. Because if lambda is equal to 0, then this means that one of x or y has to be like infinity, which is not allowed. Infinity or negative infinity. So, okay, yeah, basically, when there's a will, there's a way, right? You should be able to hopefully solve for, get rid of lambda to just get an expression of x and y, and then compare that, or, you know, plug, maybe that, solve for x and plug that into this equation and find y. Something like that, yeah? But yes, that's the idea. That's the idea. Okay, anything else? Any other lingering questions? Could maybe take another quick peek at the previous. Hold on. Yeah, no, I think doing it either way will be fine. Either this approach down here where you raise some things to the power, or this approach here where you divided things. I think either one will work out fine. Just make sure to use the third equation as well. Any other questions? Otherwise, I'll just take a quick peek at this system again, because sometimes I just have trouble, sleeping if there's still something on my mind.
All right.
But so yeah, are there any like conceptual questions at this point from either of you? I hope this like little 45-minute session hopefully gives you the gist of Lagrange multipliers. Like a lot of it at the end comes down to just playing around with systems of equations and solving, and unfortunately that's just elbow grease and staying on your toes and being aware of when you have to break things down into cases. Right, like I was saying earlier, you have to break things down into cases here where either z is 0 or y minus x is 0, and sometimes you have to decide when a case is absurd. Sometimes you do end up with genuine multiple solutions, and you just gotta, try them all to figure out which ones are maximums and minimums. Yeah. But yeah, hopefully conceptually, the Lagrange multipliers are clear. This stuff is just very dense, I think. When you have a relatively new calculus student going into multivariable calculus, most of the concepts are still intuitive and visualizable, but they're just really, really hard to read, I think. Like, it's dense. It's hard to imagine most students being capable of just sitting down and, reading 20 pages of the textbook straight.
Yeah, I think this helped a lot because it broke it down pretty well.
Yeah, that's good. Okay, let's figure out what this stupid thing, why this is eluding me. I will just want to see enough to make sure that the point here is clear. By the way, don't expect... Well, actually, you know what? For the third problem, it might not be that bad. Maybe I plugged it into a Lagrange multiplier calculator earlier, and maybe it was just struggling with the exponentials, but it honestly doesn't seem that bad to me. Problem 2, however, does seem still pretty awful, even once you know what you're doing. But I'm just trying to see if there's one particular way to cancel things out that makes everything beautiful. What if we did what if we multiplied everything here by y? So, and everything here by x. Right? So then this turns into 2xy is equal to lambda 2x plus y times y. 2xy is equal to lambda times x plus 4y times x. And then if you just subtract one from the other, you get 0 is equal to lambda times 2xy plus y squared minus x squared minus 4yx. Okay, well, at this point, I think we can just cross out lambda, because hopefully the case where lambda is equal to 0 is absurd. Which it is, because if lambda was equal to 0, then x would have to be equal to 0, which... and y would also have to be equal to 0, so that's absurd. Okay, well, at this point, you would basically get that... Oh, wait, this is actually quite... Wait, this is almost nice. Oh no, this was so close to being pretty, except for it sucks. So this is y squared minus 2xy minus x squared is equal to 0. And so this is one equation, and this is the other equation. And if we just add them together, that gets rid of y squared. Sorry, if we add them together, that gets rid of x squared. And everything at that point is left in terms of y squared or xy. Why is this so bad? Yeah. This is a very inelegant problem. Well, yeah, I think you're just going to have to go sit down and crunch out some system of equations. So, best of luck. Yeah, I probably shouldn't reveal any more, just for the sake of academic honesty. But yeah, this doesn't look pretty at all.
Thank you for